Hello students, in this video we will discuss about the proofs of application of Gauss law. So applications of Gauss law. The first application is electric field due to a line charge. Suppose this is a line charge to which positive charge is given, and this is infinitely long, so on both the sides will show up to infinity. And if we consider the particular length of this line charge, suppose we consider only length L of this line charge, then we'll get the Gaussian surface in the form of cylinder. So I explained you earlier that the Gaussian surface of the line charge is always a cylinder. So this will be the Gaussian surface, and we observe that there are three surfaces. First surface is this face of the cylinder, second surface is the second face of the cylinder, and the third is curved surface of the cylinder. And if we consider, let lambda is the charge per unit length. I explained you about this in my previous video. So this is the charge per unit length, and we know that there are three surfaces in this cylindrical Gaussian surface. First is upper surface, second is curved surface, and third one is lower surface. Suppose if we consider, for the proof, if we declare this upper surface as surface number 1, curved surface number 2, lower surface as surface number 3, then we can say that the electric field at all three surfaces is always towards outside because of line charge. So this is line charge. The electric field at this point will be away from the positive charge, and the area vector, if we consider area vector as vector dA, it will also be away from this line charge. Suppose if we take certain area and this area is dA, so area vector direction is always towards the normal to this surface. If we take a small surface, then if small area is dA, then area vector at this place on the circumference of this cylinder, it will be represented by vector dA. So the direction of vector E and vector dA will be same. Now if we talk about both the faces, because this is line charge, so the direction of electric field intensity will be similar to this as on the surface, curved surface, but the area vector will not be similar to this because the area is this. So if we consider area vector for the upper face, it will be vector dA. Similarly, vector E will be in this direction, and the area vector will be normal to the face. This is face. Normal to the face means 90 degree to the face. This is 90 degree, and the normal to this face is 90 degree to this face. So the angle between area vector and electric field intensity on both sides of the faces of cylindrical Gaussian surface will be 90 degree. The angle between electric field intensity and area vector dA will be 90 degree on the faces, but on the curved surface the angle will be 0. So for this theta will be equal to 0 degree, and for both the faces theta will be 90 degree. Now if we consider first, we are making separate diagrams to understand more clearly. On both the faces, if we talk about upper surface means we have considered it as surface number 1. This is surface number 2, curved surface, and lower surface number 3. So we are talking about surface number 1. Surface number 1 is upper surface, and in the upper surface we have seen the direction of electric field intensity is away from line charge. So it will be vector E, and the area vector is perpendicular to the face, means normal to this face, upper face. So this is vector dA, and the angle between them is 90 degree. If we talk about the curved surface, means surface number 2, curved surface is surface number 2. So area vector and electric field intensity will be in same direction, means if they are in the same direction, then theta will be 0 degree. Third one, if we consider the lower surface, means the third surface of cylindrical Gaussian surface, then the electric field intensity will be in this direction, means away from positive charge. And we are talking about the lower surface, means the normal to this lower surface will be like this. Then the area vector, the angle between area vector and electric field intensity, 90 degree. So we have got these three conclusions based on this. Now flux phi, flux is represented by phi through Gaussian surface will be, अब क्या करेंगे हम लोग, सारे तीनों फेसेस का अलग अलग जो फ्लक्स है वो ऐड करेंगे और इंटीग्रेशन साइन का यूज करेंगे. सो इंटीग्रल ऑफ surface number 1 will be vector E dot vector A vector dA plus integral of surface 2 vector E dot vector dA plus integral of surface number 3 will be vector E dot vector dA. Initially the formula for the flux, we have added the flux. Initially they look similar, but the difference is due to the angle between the electric field intensity and the area vector. Now if we move in the next step, then what we'll get, we have to leave this vector form. So it will be vector E dot vector EA vector dA will be E dA cos theta for surface number 1. For surface number 2 it will be E dA cos theta, plus for surface number 3 it will be E dA cos theta. Up to this step they look similar, means total flux will be the addition of the flux of all the three faces. Now we know that for first phase means this was the first phase, upper surface is first phase, the theta is 90 degree. So in place of this theta we will put as E dA cos 90 degree plus vector plus integral of surface number 2, it will be E dA cos 0 degree, because there is 0 degree angle between vector E and vector dA, because they are parallel and they are in the similar direction. That's why it is theta is equal to 0 degree. So for second surface, that is curved surface, theta will be 0 degree plus for the third surface, the integral of third surface is again the lower surface. The lower surface is considered to be the third surface, so it will be integral of third surface E dA cos 90 degree, because for lower face it is 90 degree, for upper face it is 90 degree, and for curved surface it is 0 degree. So that's why it is 90 cos 90 cos 0 cos 90. What is the value of cos 90? Cos 90 is 0. So this all will become 0, plus it will be written as EDA cos 0 degree, plus this will be 0. The value of cos 0 is 1. So EDA plus 0. Finally, what we will get? We can take E outside the integration sign. So E integral dA, this will be the first equation, means the total flux for this cylindrical Gaussian surface will be written as E integral dA. And we know flux, according to Gauss law, flux is equal to Q upon epsilon naught, and Q is equal to lambda L, where lambda is the surface charge density. When we want the surface charge density for whole length, then it should be multiplied. Surface charge for the whole length, so it should be multiplied to L. So that's why it is lambda L. Now put these in equation number 1. So phi will be equal to, in place of phi we'll put Q upon epsilon naught, this LHS we'll put Q upon epsilon naught, due to phi is equal to Q upon epsilon naught, is equal to E integral sign dA, and in place of Q we'll put lambda L. Lambda L upon epsilon naught is equal to E integral of dA. We'll get this expression. Now, what is the integral of dA? If we integrate a small area of whole cylindrical Gaussian surface, then we'll get the total area. And what is the curved surface area of cylinder? You have learned in maths. This is the formula of maths, that curved surface area of cylinder is equal to 2 pi r L. 2 pi r L. Okay. Now, if this is r, means radius of Gaussian surface, now it will be used in the final expression. If this is r, then in place of this dA, integral dA, we can write lambda L upon epsilon naught is equal to E into 2 pi r L. In place of integral dA, we kept this 2 pi r L. The equation was same. Lambda L upon epsilon naught, lambda L was in place of Q, and lambda L is the total charge of the surface, and lambda is the surface charge density. So surface charge density when multiplied to L, and we will get the total charge. So this will be lambda L upon epsilon naught is equal to E 2 pi r L. Now we can write it as E is equal to lambda L upon 2 pi r L epsilon naught. This small l will be cancelled. E will be equal to lambda upon 2 pi r epsilon naught, or we can write it as lambda upon 2 pi epsilon naught r. This you have to remember. This is proved. This is the total electric field intensity for the line charge. Now if we want to represent in the form of graph, we already know that E is inversely proportional to R. So for inversely proportion, this, if we take vector E on y-axis and R on x-axis, then we'll get the relation, the graph between E and R in this form. Thank you.